This is a Lab3 circuit report. The purpose of this lab is to explore the fundamental principle of direct current DC circuits and resistor capacitor RC circuits using the principle of energy conservation and current conservation. Here's the models and physical principles that are used in this lab. First, energy conservation, which is loop rule. Second, current conservation. This principle states that the total current entering a junction must equal the total current leaving the junction. Third, Ohm's law. This fundamental law relates the volt, V, current I, and resistance R in an electrical circuit V equal to Ri. It describes the linear relationship between the voltage across a resistor and the current flowing through it for the ohmic resistors. Lastly, capacitor behavior in RC circuit. The voltage across a capacitor in a discharging circuit decreases exponentially over time according to the equation delta V here, where delta V sub 0 is the initial voltage, R is the resistance, C is the capacitance, and T is time. Here's the brief preview of the result of this lab. The observation and explanation of the charging and discharging behavior of capacitor in RC circuits, the determination of the time constants RC for a given RC circuit by analyzing the exponential decay of voltage across a discharging capacitor. Here's the reasoning for the using the model's assumption and physics principles. The fundamental principles of energy conservation and current conservation are essential for understanding how circuits operate. These principles are applied to both DC and RC circuits to predict, measure, and investigate. Here's the systems and surroundings. For the systems, uh, systems for the electrical circuits comprising resistor, capacitors, batteries, and the measurement devices. And so for the surroundings were the environment in which the experiment is conducted. And here's the initial conditions. For these circuits include the voltage supplied by the batteries and the resistance of the register. For RC circuits, include the initial voltage across the capacitor, the resistance in the circuit, and the capacitance value. Here's the similarity and the difference between data and model prediction. For DC circuits, the measured current and potential difference in series and parallel register configuration typically match and to the predicted value based on the Ohm's law and another law. For RC circuits, the observed charging and discharging behavior of capacitors generally follow the exponential prediction of the RC time constant model. Here's the possible error of source of error. First, measurement error, such as multimeter readings. Second, internal resistance, such as like batteries or resistor. Third is environmental factors. Here's what if question answers. First, real ammeter versus ideal simulated ammeter. Here's the differences between them. A real ammeter has a small internal resistance and may introduce measurement inaccuracy. Like an ideal simulated ammeter, which assumes the zero resistance and perfect accuracy. Effects on the circuit. The internal resistance of the real ammeter can alert the current distribution in the circuit. Here's the second one, a second what if question. Charging a real capacitor with no resistor. The ideal model predicts an instantaneous charging of the capacitor due to zero resistance, resulting in an infinite initial current. In reality, the internal resistance of the battery and the connecting wires limits our current. Here's a conclusion. By combining the theoretical prediction with the predictor measurement, this lab provides a understanding of the behavior of DC and RC circuits. It highlights the importance of the accounting for real-world factor and the limitation of the idealized model in accuracy describing the physical system.